So as I said before, we will hold questions till the panel. And so now our next speaker will be Dr. Ahmed Busnaina, who has for many years is a distinguished researcher in micro and nano electronics and sensor in the fabrication and development of devices. In addition to being a distinguished chair professor at Northeastern University, relevant, I think, to this workshop, he is also the founding director of the NSF-supported Center for High-Rate Nanomanufacturing, and so he is going to speak to us about manufacturing for sensors.
Thank you.
So I'm going to leave this here in case you
This one. Let's see. Yeah. Oops. Thank you. Well, thank you very much. This is a pleasure to be here, and my talk will be a little bit different, and you can see that I missed the memo, so it'll be a lot of technical stuff in my talk. But I will talk about a new technology for making sensors, and I'll try to explain half of the presentation about how we make the sensors, and then about some of the sensor prototypes that we have done, and talk about the difficulties, especially when you're doing two new things. One is actually you're making a new sensor, and second, you're using a new manufacturing technology to make that sensor. So you have two variables you have to juggle. So I am the director of the NSF Nanoscale Science and Engineering Center for High-Rate Nanomanufacturing. The center graduated in 2014, which means you don't have any money after that. That's what graduating means. And we're still working on sensors and manufacturing, and I'll explain that. But I worked for 25 years in top-down nanofabrication before I started the center. And so one of the motivations that we had is basically the high cost of conventional fabrication. For example, the last two fabs that are being built are in Korea, in Samsung, building a fab at about $14.5 billion. And the latest one is being built in Nanjing, China, by TSMC, which is a Taiwanese company, and that would be a $17 billion. And we thought in 1990 that $1 billion was a lot of money. It's getting to the point where it's so expensive that only about 4 companies in the whole world that can actually build these fabs: Samsung, Intel, Global Foundries, and TSMC. That's about it. The second motivation, which is really was what the center is based on, everybody was excited about nanomaterials. This goes back to the 90s, but discovery of the nanotubes and so forth, and people were using nanoparticles long before that, of course. But no one knew how to put these things together, make something useful out of them. And so when we started the center, we said, we're going to come up with a way where we can take these nanomaterials and make something useful out of them. And we thought that conventional fabrication could actually do something, but cannot accommodate all the nanomaterials. So we had to come up with a new technology that will let you print any material on any substrate. And that means you could use manufacturing using a variety of technologies. And most of these technologies are bottom up, not top down. The third one, which is a slide that we just showed, yes, and that is the IoT. I think the IoT will need many trillions of sensors, and these sensors, the IoT can only be successful if you have low cost, low power sensors, and all kinds of sensors, not just the wearables, connect cars, homes, industrial internet, and so forth. So these are the 3 motivations that we had. Wearables, of course, is a big factor, and this is the beginning of the IoT, and you can see it's about $60. By the way, the IoT projection goes all the way from 3 trillion to 11 trillion by 2025, according to the McKinsey Institute, which does not have a good track record in predicting future technology impact. So basically, you can see a lot of companies are trying to do the wearables. You have Fitbit, you have Google's trying to do the work. But we always thought that there has to be an easier way to utilize nanomaterials and actually use a very inexpensive approach to making these sensors at the same time. So we think that the printing sensors is one of the best ways to do it. But what about the current printing industry? Why can't I just buy, a 3D printer or an inkjet printer that prints electronics? You can buy those now, and they range from price all the way from tens of thousands to hundreds of thousands. Well, there's some problems with those because they have limitations. For once, even the printed RFID tags are not really completely printed. Electronics is not printed. It's still a silicon chip that's glued on the antenna. So only the antenna is printed. The second thing is that the scale, the line width, the dimensions of the printed electronics that you can print now using commercial printers is limited to about 20 micron. Some of them can go a little bit smaller than 20 micron, but it's pretty much 20 micron and higher that you can get. Now that may be useful for a lot of applications, but and I just want to remind you, 20 micron was the silicon electron line width in 1975. The semiconductor industry line width in 1975 was 20 micron. But it still has a big advantage. A printed sensor is about 10 to 100 times, costs 10 to 100 times less than a conventional fabricated sensor. They also, right now, they print one layer only, and they need to make interconnect and multi-layers in printing. And the largest printed sensors today is basically those glucose strips that you buy from CVS and Walgreens and by Johnson & Johnson. They're made in Scotland. But actually those are only, it's a strip that has 3 gold electrodes and glucose oxidase and mediator. That's about it. When we started the center, our focus in 2004, our focus for the first 4 years is to actually take the printing down using directed assembly down to about 20 nanometers, which we succeeded in doing, but that was not enough. What we wanted to do is to two more things, because we don't think commercialization is possible if you just make things small. That's good, but it's not. It doesn't make for a technology that could be used by others or commercialized by others, unless you do two more things. One, your throughput has to be much, much higher than an inkjet, so you have to be orders of magnitudes higher, 2 to 3 orders of magnitudes higher, and the cost has to be still very low. So you still have to be much, much lower than any silicon-based electronics or sensors, or conventionally fabricated sensor. And I'll talk about how we built the printer and so forth. So how does it work? So basically we make templates. These templates are using silicon wafers. These templates be like a mask. It will have whatever pattern you want. Your pattern can go all the way from tens of microns all the way to tens of nanometers. And then you put them in a solution. Most our solutions are water. This is carbon nanotubes in water, and you apply about 2 volts, 2 to 3 volts, and you assemble carbon nanotubes or metallic nanoparticles or oxide nanoparticles, whatever you're making. This takes 3 minutes, 2-3 minutes assembly, which is the inking of your template, your printing template. It's very simple. The concept is very simple, and then you print. You take it out, you dry it, and then you print your pattern. And you can do this several times. For each layer, it's additive, of course. For each layer, you have a specific template. So you can do 4 layers, 4 templates, 6, 7, whatever number your circuit designs requires. So basically, this is very simply shows what it looks like. You have the template, you have the inking, the transfer of the pattern, which is printing, and then basically you continue the cycle. The process is room temperature, room pressure, high throughput, meaning that you print the whole layer in one shot. Okay, so you don't have anything a jet going back and forth to print. It's room temperature and pressure. You can print in flexible or hard substrates. The hard substrate, I'm not covering that here because it's a slightly different process. It's a multi-scale. It's material independent. We've used inorganic materials. With the organic materials, most of them you dissolve in a solvent, and you can still apply the same process. We've tried semiconducting, and insulating materials. A very low energy consumption, very low capital investment, and you can make the whole thing using one tool. This is what the template looks like. This is silicon. We also make templates on polymers so that you can use them for a roll-to-roll if you like, for example. This shows 30 nanometer silica particles that are printed. This shows PSL particles. This shows carbon nanotubes. And by the way, one of the advantages of this technique is that aligns the carbon nanotubes during printing, during the inking process. The nanotubes are aligned, so you get a nice aligned channel of carbon nanotubes, which is very useful if you're doing sensors or electronics. We built the tool. I don't have a video here because we don't have time. But this is a cluster tool that we built, and this is the inking station. This is the printing station. This is alignment and registration unit that used to align the different layers, and this has a 2 micron resolution, and we won a variety of awards and so forth for this. But the key thing for this is that it prints 1,000 times faster and 1,000 times smaller than an inkjet. There's a lot of videos on YouTube. If you go, there's a video made by the Museum of Science. If you go from lab to fab on YouTube, this will come up, but watch out. It will say, do you mean from flab to fab? You don't want that. This was made by NSF, and this is made by one of my students. So they'll show, the first two will show a lot of interviews and discussion with industry people and government people and so forth. The last one will just show a sequence of the printing, one printing cycle. This is our newest printer. Actually, it's being built right now. And so we went away from the cluster tool, and we went to linear because now we have, as you can see, 6 functioning modules with input and output. And so now we added a annealing and inspection station to the tool. So this is being built right now. The purchase order is out. We use this technology to print metamaterials, shielding, energy harvesting, flexible electronics, interconnects, NEMS, a lot of sensor work, and even printing drugs like paclitaxel. And also take insoluble drugs and make them soluble, for example, by printing them in rod shapes and different shapes and so forth. And most of these drugs are printed less than 100 dimensions, less than 100 nanometers, because it turns out that if you print a drug particle in a rod-like shape, it would have about 10 times. It would be 10 times more effective in penetrating cells than a spherical particle. This is some of the example. I'm going to run quickly through some of the examples of the sensor. I'm going to have a couple of slides on a chemical sensor designed to detect hydrogen sulfide. These are a sensor for detecting E. coli, bacteria, and viruses. These are all carbon nanotube-based sensors. This sensor is for detecting glucose and lactate using sweat. This is actually a carbon nanotube on a chip, and this is for alcohol detection. This is for cancer detection. This uses nanoparticles, not nanotubes. And these are some of the electronics that we make. So I'm going to show 3 examples, and we'll show one slide about the electronics first. So the electronics, a lot of the electronics that we did print are using 2D material like molybdenum disulfide, using electronics using carbon nanotubes and molybdenum disulfide to make inverters and so forth, using carbon nanotube transistors. But remember, you don't have, if you do electronics, you don't have to use that. You could use that, but you don't have to use that. You could use silicon. You can use gallium nitride. You can use gallium arsenide. You could use zinc selenide. You could use any 35, 24, 26 semiconductors. And they work, actually. We printed them, and they work fine. Sensors, I want to just go through some of the issues that we deal with sensor, because we are manufacturing, and we use the sensor as a platform to verify what we do. So the first thing that you run into when making the sensors, which is the same thing if you make electronics, is scalability. How big of a substrate you can handle. Most students work in the lab with a small chip and so forth. Now we want our newest tool will go up to 12-inch, for example. Reproducibility. How do you ensure that? And how do you ensure high yield? The raw material supply, and I think was mentioned, the carbon nanotubes, of course. That's a huge issue that has to be dealt with. The yield, the life cycle of the product that you have. What is the life cycle? How does it compare to others? Packaging. That's a big deal. You know, is it supposed to deliver liquid to the sensor? Like, for example, if you have sweat, or the packaging is supposed to take the sweat and take it to the sensor and then wick it out. Well, how do you do that? That's a different project altogether, you know. And the sensor system, what is supporting electronics? Most of these sensors are analog, like you mentioned, you know. They have to go to a digital, and then you have to send them somewhere else. You know, you have to communicate that. The sensor itself, it has to be very specific, otherwise it's not really useful. It has to be repeatable and stable from batch to batch in different environments. Regeneration, especially if it's a biosensor, how many times can you use it? How long can you use it? What's the shelf life? Response time, does it take a few minutes to give you a signal, or does it give you a signal right away in a second? Signal strength, that's very important. If you're doing a wearable and your signal is 10 nanoamps, forget it, you know, that's not going to work, because it will be drowned by the noise from the other electronics that are nearby. Testing and characterization protocols. How do you test it? Especially if you don't have any protocols. For example, we do testing on glucose in sweat and lactate in sweat. Well, what other protocols? Well, there aren't any yet, you know. so you have to make your own and talk to other people that are doing the same thing, and try to because if you're going to commercialize this, whoever is your customer is going to actually have to say, well, I have to have sensors and I want to test these sensors myself. Well, do you know how to test them? No. Well, so you have to protect. You have to have these protocols developed so that when you have customers, do that. This is something that the first two speakers talked about, is that how do you commercialize it? You know, you have a technology and you're trying to push it on different people, and they're not receptive. Say, well, I don't think I want that. So basically, when you have a new technology, it's like push and pull. The I-Core program, the NSF I-Core program, did a very good job, because it tells you, forget about the technology. Go to customers and ask them about what is your pain. Which is the same thing. Right now, we started with a lot of sensors, and then when companies come to us, they tell us about their pain, and we're sort of moving in a different direction, because basically they want something that they cannot get, and we don't know that, you know, but they tell us that, and so that actually is very, very helpful, especially if you have a startup or you're doing research in a university. That's very, very important to talk to people who are working in the field, and they tell you what sensors they need and what the specs are, and they tell you everything. All you have to do is just make it. So I'll give you about 3 examples of sensors. They're all actually well, 3 of them are carbon nanotube based sensor. The other one is nanoparticle based sensor. This was funded by the oil industry, Schlumberger, Halliburton, British Petroleum, and so forth. And it's a hydrogen sulfide sensor that's supposed to work in a harsh environment. This is really not easy. I'll tell you why. Because if you have electronics, your electronics will not work in this harsh environment. Your diodes or transistor will not be stable at that temperature. So you have to find a way around that. And also a high pressure, 2500 psi. It has to work in various environments. It has to work in nitrogen, it has to work in air, it has to work in water vapor, in water, underwater, with other hydrocarbons, and so forth. It's a chemi-resistive, resistant-based operation. We chose a 2-terminal device channel instead of a FET, which is a 3-terminal device. Why? Because they want it to be very cheap, because they throw them on the reservoir and they probably will lose about 80% of those. So they want it to be extremely cheap, so that if they lose it, it's okay. And so the sensitivity is ppm. So this is what it looks like. For example, we have the sensor is functionalized with a molecule. You could use 4-amino tempo or tempo molecule, and the sensor has a nice thing that it recovers. So when it detects hydrogen sulfide, the resistance goes up, and so the current goes down, and then exposed to air, it recovers, and so the baseline is always the same. And this is what it looks like. It's a channel. The channel that detects the hydrogen sulfide is only 1 micron by 10 micron. And you can see, you contrast that with what you can buy now in the oil industry. The sensor is about 5 pounds and $400. And our sensor, of course, is like 50 cents, maybe, or less. The other sensor that we did is a cancer sensor. This is actually a nanoparticle-based sensor. So we functionalize nanoparticles. We assemble them in specific trenches, and we can put 4 different biomarkers here. And so this was published in Lab on a Chip. This was funded by the Keck Foundation. And you could see that it can detect cancer actually in a mouse after 3 days, where typical technology will not detect the cancer until the cancer is very visible on the mouse. And so detection limit is about 15 picogram per milliliter, and the hospitals have detection limit is 3,000 picogram per milliliter. So it tells you that you can actually detect cancer much earlier, because you can detect minute concentrations of antigen in the blood. This is the sweat based sensor. Actually, I have some samples if you want to take a look at them. And these are about 100 sensors here in this small area. And so these sensors, actually, when we first did these sensors, they looked okay. The Air Force spec was 3 days. It has to work for 3 days continuously. We did it 14 days, and it looks okay, except if you look at the y-axis, it's nanoamps. It's like 10 to 20 nanoamps. That's not going to work. So we redesigned the sensor, and you can see now this is actually this is amps, but actually it's milliamps. Amps multiplied 10 to the minus 3. So you can actually, it's an instant. The signal is instant, and it corresponds to the concentration, and very strong signal. And this is comparison with the latest research. There's no commercial products yet, and our sensor basically has 2 features. Here, for example, that it does not see the other sensors are all in the nanoamps. Our sensor is hundreds of microamps or milliamps, and all the sensors require adding a mediator, a chemical. We don't. So it's a very unique feature of the sensor. It's still a carbon nanotube. Also, they enter batch sensitivity. So we follow the batch. This is what the sensor looks like with long yields. We ship this to lots of companies to test. And so they require that the yield have to be far away so that when they bond them, they don't damage the sensor. And you can see that this is there is some variation from batch to batch. And this is basically when you do small batch, you always have that because the condition changes from day to day. So this is something that by automation, by the new tool that I showed, where it's fully automated and the recipe is stored there, that will be less of a variation in the sensitivity of the sensor from batch to batch. The same sensor was used to detect, this is in water, detect bacteria, detect viruses, and also detect pharma products in the water. There's a lot of pharma products in the water, drinking water, that is not actually taken out by the water treatment plants. So actually we develop sensors. These are threshold sensors that tells you if you have a high concentration or not. And so at the end, I just want to summarize. This technology has been developed, funded by the National Science Foundation, and it lowers the cost by about 10 to 100 times, prints faster, 1,000 times faster than inkjet-based printing, and 1,000 times smaller. A variety of benefits. It makes printing sensors and electronics extremely inexpensive. And the printer we have is a TRL7 and MRL7. And the printed sensor right now, the sensor itself, not the electronics, is about TRL6. And we have actually the center filed about 100 patents. We have 35 patents that are specific to what I talked about. 20 of them have been awarded, and we just started a company to actually make these printers available to everyone. And but we also, at the same time, we're printing wireless sensors prototypes for small, medium, and very large companies for their testing. And I'll stop here. Thank you.
Thank you very much. So we're a little bit behind schedule, but not that bad. So I suggest that we go ahead with the break. We'll come back at 10 after 11. So we'll be a little bit, but not much behind schedule. And at that time, we're going to have all of the speakers, or almost all of the speakers from this morning and also this afternoon, to sort of come to the front of the room to nucleate a conversation about some of the issues that were discussed this morning, but we'd also probably expand into some of the things that we plan to address this afternoon about testing. There's coffee outside. For later for lunch, there's a list of all the places on the table outside, a map of places to eat, and there's also some places nearby if you prefer, Dunkin' Donuts or Starbucks coffee. And the time right now might not be that bad. You can make it back in 20 minutes, but that's a warning that you might make it back in 20 minutes. So we'll see you all.